Hello everyone. Today we are going to see definition of linear transformation. So chalo, let us start. Let V and W be vector spaces, then a function or a map T from V to W is said to be a linear transformation if first T of 0V is equal to 0W. Next, T of u plus v is equal to T of u plus T of v. This should be true for all u, v in vector space V. So remember, this u and v are from what? Domain. Next, T of alpha u is equal to alpha times T of u for alpha belonging to R and u belonging to V. So this is also true for any alpha belonging to R, means any real number alpha and any element of our vector space V. Just note one thing, whatever this first condition is there, this is not at all needed in order to show a function is a linear transformation, but this first condition can be used to show that the given function is not a linear transformation. So my point is, if you are having a linear transformation, then 0 is always mapped to what? 0. So this 0 to the suffix v over here, whatever I have used, it indicates 0 of this vector space V, that is our domain, and this 0 of W indicates 0 of this our codomain of a function. So these two conditions are important. Means given a function, we will check this first condition. If this first condition is true, means if 0 is mapped to 0, then we will go for what? Second and third condition. If 0 is not mapped to 0, then we can say that T is not a linear transformation. So in other words, this first condition is used to show that a function is not a linear transformation. I will repeat again, if T of 0 comes out to be equal to 0, then we are supposed to go for second and third condition. If second and third conditions are true, then the given function will be a linear transformation. Otherwise, it will not be a linear transformation. Remember, second condition is saying that T of u plus v should be equal to T of u plus T of v for all elements u and v from our domain V, right? The second condition is saying T of alpha u should be equal to alpha times T of u for all alpha belonging to R and u belonging to V. Now note, these two conditions can be combined together into a single one. So mostly we will use this condition in order to check or show whether the given function is a linear transformation or not. So what this condition is saying, T of alpha u plus beta v should be equal to alpha times T of v plus beta times, alpha times T of u plus beta times T of v for all alpha beta belonging to R and u comma v belonging to vector space V. Now let us go towards some examples. So first, now see here, for this particular example, what is our domain over here? It is R, so I will call it as V. So I will say here our domain V is equal to R, and what is our codomain W? That is also R. So what is our 0 of V? That is our domain, that is our usual 0. and 0 of this w is also our usual 0. Now we'll go for this first condition, right? This first condition. So t of 0v will be equal to what? T of, now 0v is our usual 0, which is equal to, now try to use this definition of the function. So what will be our t of 0? It will be 0 plus 3, which is equal to 3. So is it our 0 of w? Not at all. This is not equal to 0 of w. So this first condition is failing, right? So therefore we can directly say that T is not a linear transformation. So this is the beauty of this first property. Now we will go for the second example. If our T is from, say, R2 to R2 defined by T of xy is equal to some x plus 1 comma y plus 2. So here what is our v? The domain, we call our domain as v, right? R2, and our codomain is also what? R2. So what our zeros? So our zeros are 0 of v, you know 0 of R2 look like this, and what about 0 of w? It is somewhat like this, right? Now we will go for our first condition. So t of 0v is equal to what? T of 0 comma 0. Now what is t of 0 comma 0? Try to use this definition of function. So it is 1 comma 2, right? And which is not equal to what? 0 of w. So again this first condition is failing, so therefore t is not a linear transformation. Okay, now we will go for some more examples. The third one, suppose my function is from, again I will take it from R to R, defined by t of x is equal to some x square. Now over here our v is R and our w is also what? R. Our zeros are 0 of v is usual 0 and 0 of w is also usual 0. So the first condition, what will be t of 0v? It will be t of 0, which is equal to what? 0 only, and that is our 0 of w, because t of x is equal to x square, therefore t of 0 will be 0 square, but which is 0 again. Now the first condition is satisfied, so we cannot say that this t is a linear transformation here itself, because the second and third conditions should be satisfied. Okay, now we will check the second condition. Remember, for the second condition we need two elements of the domain, that is our R over here, this one, and for the third condition we need one element of R, that we are calling it as alpha, and one element of our domain, that is our R in this case. Okay, so over here I'll take two elements, I'll call them as x and y from the domain. So I'll say let x and y belonging to V, that is nothing but our R, be any element. Okay, so therefore what we have to check actually over here, for the second condition we have to check whether this t of x plus y is equal to t of x plus t of y or not. Is that fine? So we will start with LHS. So LHS is t of x plus y, which is further equal to, so my t of x plus y will be what? See, t of x is x square, so t of x plus y will be x plus y square, and this will be equal to what? X square plus 2xy plus y square. Now this is about our LHS. Now what about our RHS? Our RHS will be t of x plus t of y, right, which is further equal to, so t of x will be x square and t of y is nothing but y square. So observe this star and double star properly. So what we can say? We can say that therefore this t of x plus y is not equal to what? T of x plus t of y. Therefore the second condition is not satisfied. So therefore this is not a linear transformation. Now observe that after the first condition, this one, okay, yes, after the first condition, we go towards what? Second and third condition. But as I have told you before, these two conditions can be combined into what? This one condition only, right? This one. Okay. So what I will do is, hereafter, instead of doing this calculations for 2 and 3, I will do calculations for only this one statement, right? So our calculations will be reduced. So now we will go for some examples.